Okay, it's past 5 minutes, so I'm gonna go ahead and start. So thank you everyone for coming to the end of the search program presentation bash. Here, so we don't see it. Okay. Okay, so if this is the manifold of the humanities knowledge, I'm going to use Matt Might's analogy from his blog. Basically, when we are in primary school, we start developing in all directions to get knowledge, and in high school, we just add more, to that ability of basically understanding everything. And the Bachelor of Science is a time when we sort of start specializing, so we're no longer developing in all directions. We kind of pick a direction that we're getting more and more experts in. The master's program really makes you push further on that direction. And then eventually you reach in that particular direction the area where the knowledge of humanity stops. And if you zoom in there, you hope to make that tiny increase in there, and normally that's called a PhD. But in this program, you basically did the equivalent of that. So, of course, the problem is that you kind of have to cover this path that we normally gradually reach by doing a master's and a PhD to make that dent in a summer program. So that takes a couple of special things to happen. First, it takes a special project for which your mentors have to think kind of deeply about how they're going to structure that project so that it can be reached like that in an accelerated fashion. And then it also takes very special students to be able to be willing to actually engage in that super accelerated path to the edge of knowledge. And when we're doing this project, when you're working on your program in SURF, you're sort of thinking of your, you're pushing against its boundaries very hard. But in the grand scheme of things, this is sort of how it looks. So it's okay if you feel like, oh, okay, this project, I've made this, tiny progress, because that's pretty much how all research projects work. We just push tiny bits in one direction. So there's also this aspect that most actual results tend to be kind of boring because we have to overlap with this Goldilocks scenario where we have the possibility of actually producing the new information, and by the time you have the possibility, you sort of predict you're going to have the possibility, so it becomes a bit boring. Like you ahead of time, you think, oh, this is going to work out. So like, student is going to work on it, and we try it. So then it's, the awesomeness characteristic decreases a bit. But we should always keep the perspective that, we are basically thinking about the universe, and we're thinking about how we can study it better. And this is a sort of privilege because funding for SURF comes from taxes. So, NSERC, thank you, NSERC. And there's also sort of a zero-sum game when it comes to funding research, which is that whenever you fund one research, you technically don't fund something else. So you always want to be very purposeful and take responsibility for how you're using that funds, and basically making sure that you are doing your best with the research problem that you're pursuing. And okay. Yeah. That's the wrong laptop. I'm sorry. Okay.
Thank you.
Yep. And yeah, sure. Okay. And then in addition to that, this is an oversubscribed program. It's about 7 per 1 spot. So no need to feel imposter syndrome. We really wanted you to be here, basically, because we had so many people to choose from. So congratulations for going to the program. And also, we are also very lucky that we don't suffer from, we're not in a war zone, we're not in very dire situations. We can actually focus on these things. So this is what I call never be so smart that you forget to be kind. But then also, there's people who we allow to basically have buildings and water and own them completely, and we should always ask for more. Basically, we should ask for more funding for science, and we should ask for better conditions in life for everyone. So that's what I call never be so kind that you forget to be smart. But in general, basically, always try to make the situation better for the world around you, and ask for the people who can make it better to also do it as well. And this is a Taylor Swift quote, by the way, in case you're not familiar with the repertoire. So research progress in general, when you start the program, you sort of think of it in like, oh, I'm going to have 16 weeks, 4 months, and I'm going to make a gradual nice increase on it. Well, it doesn't actually work out like that. Somehow even an extra month appears in there, sneaks in there. So it's okay if you feel like you have like very big roller coasters of productivity. Sometimes you go back and like, oh, I had a bug, this completely doesn't work. That's the normal experience. And this is taken from the PhD experience blog. I modified it in the original thing. This is years, 1 year, second year, fifth year. So yeah, that's kind of what happens later. So in that sense, we do manage to give you like a view of what awaits so that you can feel like if you like it or not. And in this program overall, when you're doing research, there are so many different skills and different tasks that you kind of have to grapple with. So this is, again, normally done for a PhD experience, but I really think that it fits quite well for this project as well. You will have gotten through all of these stages in 4 months, but probably you've done maybe 60% at some point, like your path brought you to about 60% of these tasks. And right now you're in this Goldilocks zone of science communication. That's your task for today. And just want to point out that in the analogy of the manifold, where you're just reaching the boundary of humanity, all of you now have gone in basically different directions and have reached this boundary to different paths. So this creates an opportunity for you all to learn from each other, and I can't wait to hear what other students have basically worked on. And I'm not going to give you instructions on how to present because you already made your presentations, that's done. But I just want to give you like a heads up of sort of how to get the most out of your peers' presentations, which you're going to be sitting through for the next 2 hours or so. So you can do what's called active listening, where you're trying to always be in conversation with yourself. This is something I got from Dick Bond. So you try to basically always be in tune with the presenter, and even if you don't understand what's happening, you just continue talking with yourself in relation to the presentation, which is thinking, oh, okay, wait, why are they doing this? How do they do this? What I could ask, what's the main thing I don't understand? What's the message I do understand and I want to remember? If you take that down. So basically, take notes of the important messages you understand. Taking notes helps you assimilate the knowledge simply from the act of writing them down, even if you don't look at them later on. And write down if you have specific questions that come to you as the presentation progresses, and then obviously ask the questions at the end as well, if you feel comfortable. And there's a saying that no question is a question, but here's a list of very good questions in general. So always try to understand why they're doing it. Because like we said, because of the funding situation, there's always basically reasons for which someone embarks on a specific research project. There's a pot of gold somewhere that they're trying to reach. So try at least when you finish the presentation to think, okay, I know why these people worked on this for 4 months. Like the point was for them to try to understand this. And if you don't understand, that's fine. Just ask them at the end. Try to ask the right question so you get that for yourself. And then other specific questions, if they're working with inference from data, you can think of alternative data sources and understand why they chose to use the specific data set versus others that you may be aware of. And maybe you know that there's something else that could be useful. And I've heard this at conferences so often when people say, oh, but have you considered using this other satellite data? And like, oh, this can be useful. So you actually can give people help. At the end, try to analyze the technique. This is the hardest part in presentations, to understand the methods that people are using. Usually they involve a lot of math, so equations are being skipped. But nevertheless, try your best. Maybe you already know conceptually what the technique is. Maybe you know PCA because you already studied PCA, so even though it's not presented in it, you know it yourself. So you can think, oh, but there's alternatives to PCA. Maybe they should have used this. So try to basically have that analysis as the presentations are happening, and then always look for the limitations of the results and the technique used, and try to understand what they are. And then someone is working on pure theory because we are the Center for Theoretical Astrophysics. So there's always a good question to ask whether or not that's ever testable. Sometimes it's no, that's okay. It's more like a math application technique. But if it is, it's very nice for you to understand what this is for, actually. So also I want to give a shout out to the people who make search possible, in addition to the funding that comes from NSERC. The CITA admin and tech staff, the CITA director Peter Martin, Professor Murray, who helped to lead the class, and two faculty who helped with the class. I'm not sure who they are. I don't know if it was Maya and Victor Part. I'm not sure who it was in the end, but thank you if you helped with that class. And then the SURF mentors and mentees, some of which are faculty, postdocs, or grad students. So with this, the future brings in a near future a lot of amazingness as you're going to present your awesome research. And I think the best thing to do would be either, if you already have the slides, come over. If you have your laptop, you can also come provide your laptop.
They're all in one presentation.
Oh, okay. Do you want to load that in a Zoom meeting?
I thought you already have it. I'll email it to you.
I don't have it. Okay. So I guess I'll log into my account so that we can share it from the CITA. I knew I shouldn't have logged out yet.
Should be in your inbox.
Okay.
It's a bit cumbersome to try to extract it, but it's
Okay. Thank you. Let's see if this works. Safety comes after us, but the most critical moments. Okay. Share. Okay, can people online see the search presentation deck right now? Can we get the... Yes, okay, great. So, yeah.
we're gonna need someone to explain to us to move the slides. At least for those that are online.
With my what?
So Arian is online.
Yeah.
We need someone to move the slides.
Oh, okay.
I can do that.
Okay, thank you.
Like,
Okay, Aryan, can you hear us?
Yeah. I had the same question. Yeah.
You have what?
So how will I control the slides from here? That's the question.
do you want to share your own?
Yeah, maybe you have your own. that's
Yeah. I'll do that. I'll share it from my screen. Yeah.
And then we'll switch back.
So, okay. Great.
Thank you for the introduction.
Okay. Is it visible?
Yes.
Okay. So, hello everyone. My name is Aryan. I'm a third year student at the University of Toronto, and today I'll be presenting on my summer research project on deciphering the structure of molecular clouds with neural networks. The project was supervised by Martha and Shivan. So to understand the project and to understand what molecular clouds are, we need to understand what the ISM is. So unlike general consensus, the space between stars is not empty. It's actually filled with dense chaotic gases that over time form filamentary structures. There are different mechanisms that lead to the formation of those filamentary structures, some of which are gravitational instability, radiative cooling, and self-gravity. Now those filamentary structures lead to the fragmentation of gas, and that fragmented gas clouds lead to the formation of giant molecular clouds. It's those giant molecular clouds which are the focus of our study. What we aim to do in this analysis is to develop machine learning models to aid observational studies of GMCs by trying to predict quantities which cannot be predicted observationally. The way we do this is by using galaxy simulations. And within those galaxy simulations, we implement clustering algorithms such as Cloud Finder to create cloud clusters within those galaxy simulations. And it's those cloud catalogs that form the input to our data and our training data in the machine learning models. So before we get to the machine learning models that we trained and the results we got from that, it's important to understand what the simulations are, what the Cloud Finder algorithm is, and what kind of data we get out of it. So we used the Fire2 simulation. It's a simulation that creates Milky Way-like galaxies. And within those galaxy simulations, we implemented the Cloud Finder algorithm. So the Cloud Finder algorithm works by using density peaks. So the way it works is it uses virial parameter and density peaks to cluster particles, and those clustered particles forms our cloud catalog. So from the images that we see here, from the plots we see here, we can see that the virial parameter stops at 5. This is because that was the condition that we gave to the cloud finder algorithm. One more interesting thing that we can observe is that majority of the clouds are low mass clouds, like not exactly low mass, but have a mass of about 10 to the 5 solar masses on the log scale. Another interesting diagram that we see here is of the log densities. It's the difference between the particle densities and the mean particle densities of every clouds. Theoretically, from the papers that I've read and from the papers that are available on molecular clouds, this follows a log normal distribution, which tails off on the positive spectrum as a power law. So this gives us a basic understanding of what the data looks like. Now moving on, once we understand the data, we define our models. So we use supervised learning to develop regression models, and those regression models predict quantities that cannot be observed observationally. We used three networks. The best performance we got were from neural networks, and that's why the results that we show here are mostly of neural networks, are all of them are of neural networks. The quantities that are of interest to us are the 3D volume densities, the shape of the PDF of cloud densities, and the 3D dispersion velocity that we calculate using those neural network models. So the model inputs that we use are the galactocentric radius, which is basically the distance of the cloud centers from the center of the galaxy, the 2D surface density of the clouds, and the dispersion velocity or the line of sight velocity of the clouds, which is basically the dispersion velocity along the z direction. So all of this is sent as an input into a neural network, and the neural network has a, a X number of hidden layers, and in each of those hidden layers, we have activation functions that introduce some sort of non-linearity into the system, and the network gives us a prediction, which then uses mean squared error to backpropagate and change the weights and biases so that we can minimize the error. So one quick analysis that we did decided to before we decided to create the models is to test, is the model architecture dependent the model performance dependent on the model architecture. And what we found is that the model architecture doesn't really depend on the results. So this is basically a plot of different number of hidden layers on the y-axis and the different number of average neurons that we have in each layer. And what we see is that the mean absolute percentage error doesn't change much based on the number of layers, the hidden layers we choose, and the number of different neurons we have in each layer. So we can be rest assured that it doesn't, like, the model architecture doesn't depend much. It's the correlations the model has with the input and the output data which matter the most. So the first model that we worked on, we tested with, was the 3D density model. And the 3D density model did give us good results. It had a log scale error. So that meant that for smaller values, for smaller predictions, the error was very small. But as the predictions went to higher values, the error also increased. And that's why it can be seen that the mean absolute percentage error in the linear scale is high, but still we get a very good line of fit. So this plot basically shows the actual versus the predicted data. This data that we have given is of the random forest, but it works the same for the neural network as well. We get the exact same results, and we can see that it follows the line of best fit. So what can we tell from the 3D density model? What we can tell is that the model is very accurate for smaller values, and from the histogram of 3D densities, we do see that most of the clouds have a very small 3D density. And this means that on average, if we test the model on observational data, we should be getting good results out, given most of the densities are still going to be small. So we should be getting good results out. And that's what we observe. What we observe is that when tested on observational data, and when we have a map and we have a plot of the input data and the output data. So in these two plots, what we have is the y-axis showing the volume density, which is our data that is of our interest, and the x-axis showing the different inputs that we have. Both the plots have data in their normalized units. So we don't have the data in its actual units. It's normalized, and we have taken the log of it. But what we can see is that the data learns the distribution from the training data. So the right side shows the simulated data and the left side shows the observational data. And we can see that even just for one of the two quantities, it was able to learn the distribution of the simulated training data. The next model that we worked on was the variance model. The next model what we worked on was defining the shape of the clouds. So the way we defined the shape of the clouds was with a quantity S, which was basically the log difference of the cloud particle densities and mean cloud particle densities. And the other quantity that we used to describe the shape of the PDF of the density model was the difference between the 84th and the 16th percentile in the logarithmic scale. Why did we use this kind of measure is because if we go back to the plot on the uh, the density of the cloud particles, what we see is that each and every peak represents S, and the distribution basically explains the variation in the cloud particle densities. So when we get the results, what we see is that the variance model and the mean model do not perform up to the mark. Uh, and even though their error is similar to the 3D density model, the plots that we see are not very good. We don't see a good line of fit. And the same goes for the mean model. What happens is that both the models learn the mean of the distribution and have some sort of a scatter, but are not able to learn a distribution that can fit the line of best fit. So uh, our reasoning of why this doesn't work is because of lack of a strong correlation between the mean and variance with the input quantities. The 3D density model had a very good line of fit was because the 3D density has a strong correlation with the 2D density, which is clear from this plot. in both the cases, in both the observational and the simulated data, the 2D and the 3D densities have a strong correlation, a strong positive correlation. But that sort of correlation misses in the variation, in the variance and the mean model. So moving on, we tested this with the 3D velocity model. This is because the 3D velocity dispersion has a very high positive correlation with the line of sight velocity dispersion, which is basically the velocity dispersion in the z direction. And what we see is that the model performs good. We get slightly higher mean absolute percentage error compared to the uh, 3D density model, but we do see a good line of fit along the z-axis with some increased error as we go towards higher velocity dispersion. And when we test it with observational data, we do see that the results match a good amount with the input data. So what we see is that if as long as there is a strong correlation of the output data with one of the input datas, the model performed good and gave us good results. Uh, what what you would like to conclude is that our analysis has given us a direction to work on more such machine learning models to aid observational studies of molecular clouds, which could help many researchers in this field. The kind of work that we want to do in the future is first trying to solve the problem of renormalization. All the data that was presented here was in the normalized scale for both the models. This is because the range of the simulated data and the range of the actual observed data is unknown. So we cannot renormalize the observed data the way we would if we were able to renormalize the testing data after training it with the same data set in the simulated data. A potential solution to that is using Z-score normalization instead of the normal normalization we used, because Z-score normalization would take an assumption that the underlying distribution of each input with every output is similar, and we can use the same standard deviation and the same mean for the observational data as well. So I would like to conclude my project here and thank my supervisors again for giving me this wonderful opportunity. Thank you.
Here.
Next presentation is also.
Oh, okay. Yes.
We want to take what are there going to be questions now?
Oh, yeah, questions. What's the matter? Yeah, so do we have any questions for our first presenter? Zero. Or online? Yeah.
I have a question. So thank you for the nice presentation. Can you hear me? All right.
Yeah, sure. Yeah, I can hear you. Yeah.
Great. Thank you. So I was just wondering what if you had any ideas for. Apologies if I missed it, but next steps, like how you might extend the algorithm to include other input data or to target other systems. Have you guys talked about anything like that?
So we didn't quite talk about that. One thing that was in our mind, if we had more time, was using unsupervised learning methods. So initially, at the beginning of the project, we were working with variational autoencoders to basically get the structures of the 3D, basically get the 3D structures of the clouds, given we can only observe the 2D structures. That project didn't quite work out. That site didn't quite work out because it got very complicated in the initial parts. But that was something which was on our radar if we were able to get the observational data tested early on and we had a couple of weeks or some more time in our hands, if we had some amount of time there. But since we got the observational data late and we made those models late, the more important problem towards the end became the problem of renormalizing and getting all the data in its original scale. So still, even the data that I presented here is not in its original scale. It does follow the distribution that the model learns from the testing data, but it is not in its original scale. I cannot say that, okay, this is what the data should look like given it's in the original scale. This is a big problem that we are trying to solve. Let's go statistics is something which we can try probably tomorrow since it's the last day. If maybe if you want to do that, but yeah.
Thank you.
Okay. Have any other questions? Yep. Mark?
Maybe to follow up on that, how generic is your method? You now managed to find clouds or blobs. What if I wanted to find some geometric feature in a magnetic field? Could you apply the same method?
So from what I think, as long as there is a correlation of one of the data, let's say we are trying to predict the magnetic field along the Z direction. Uh, uh, like to be honest, I don't know much about magnetic fields, the study of magnetic fields, but let's say we are trying to predict some quantity related to magnetic fields, and we have some inputs on which we want to train a regression model. As long as there is some correlation of the input quantities with the output quantities, we should be getting a fairly good model. But it, of course, depends on the specific model, the kind of data we have, the kind of data cleaning methods we use. But I think in general that should work if there is some underlying distribution that the model can learn. Because given neural networks are very powerful in learning even the most non-linear kinds of distributions, I think we can generalize this.
Thank you.
Great. Okay, so we have to move on. So if you can start sharing your slides now, and you have 10 minutes, and I'm gonna start keeping track of that now. Yeah. So Andel, can you hear us?
Yes, I can hear you. Can you see my screen?
Can hear you very well, and we can see your screen. So you're
Perfect.
good to go. Yeah.
So, hi everyone, I'm Andal. I'm a third-year student at UBC studying computer science and physics. And today I'm going to be presenting feature extraction algorithms for Newton-star equation of state. And my project was supervised by Reed Essek and Oscar Shmali over the summer. To break this down, we first need to understand what neutron stars are in the basics. Neutron stars are supernova remnants of high mass stars with canonical radii of 10 to 15 kilometers and masses of about 1.4 solar masses. Unlike main sequence stars, they mainly sustain their equilibrium by neutron degeneracy pressure and nuclear interactions, which we don't fully understand, against gravity, as we'll see later. And what's particularly interesting about them is that their core densities can be as high as 6 times the nuclear saturation density, which gives rise to some interesting behavior at the particle level, as I will present later. The second thing that we need to understand is the equation of state and the TOV equation. The equation of state is a function that relates the energy density and pressure of the star. For a given neutron star equation of state, we can solve something called the TOV equation, which we can think of as a map that takes in a given equation of state and then maps it to more macroscopic properties like mass and radii, which in turn can give us quantities like moment of inertia, tidal deformability, which we can explore more later. And the third thing why all of this is particularly interesting is that currently Newton's star equation of state remains largely unconstrained because we don't have fully developed theoretical models, and every model that is presented assumes some underlying composition of the matter inside the course, which is debated, again, to begin with. But the main thing that we need to keep in mind is that if I give an equation of state and I solve the TOV equation with it, I can obtain these more macroscopic observables like mass, radii, moment of inertia, etc. The third thing that we need to understand in particular for this project is phase transitions in neutron star matter. Several models propose that while we understand what happens in the outer layers of the neutron star, we don't fully understand the composition of matter in the more inner cores because densities are very high at those scales and nuclear theory is not fully developed at those densities. And we suspect that hadronic matter in the inner core transitions to more exotic phases to support pressure. And some examples are like quark-gluon plasma, hyperons, mesons, and we believe that such phase transitions manifest as sudden changes in something called the sound speed, which is denoted by CS here in stellar media. So precisely the speed with which pressure waves propagate through stellar fluids. And in turn, what we're trying to primarily work with is the effect of these phase transitions on more macroscopic variables. So things like mass, radii, and inertia. And we're trying to build an algorithm that can work our way backwards to constrain the true equation of state given certain MR curves that we can get from observational data. So to do exactly this, Reed and a team of researchers last year proposed a feature extraction algorithm to detect these phase transitions directly from more macroscopic relationships. And the main idea was that if you give an equation of state, they propose that there exists a feature D, which is sensitive to kinks in these more macroscopic relations, which can then be mapped back to more microscopic physics. And D was defined as the logarithmic derivative of the moment of inertia with respect to mass, parameterized by central pressure. And what they actually ended up plotting was arctan D versus M, because they wanted to map it to a finite interval, and it seemed to aid in characterization of features. And because each phase transition is characterized by some onset density and some ending density, the ending densities of phase transitions seemed to be correlated with the presence of local minima in this feature space that we defined. And the onset densities were then detected for each ending density by finding preceding maxima in the sound speed space. But what we're particularly interested in and what the algorithm mainly does is identify the endpoints, because that is what we're doing primarily from the macroscopic relations. For example, this is one of the demos for a given equation of state. On the top left, you have the equation of state space where pressure as a function of energy density is plotted. Then this is solved with the TOV equation to solve for a more macroscopic relation like mass and moment of inertia. And then this is then mapped to the arctan D M space, where you can see that there's a sharp local minimum with the leftward arrow, which is then to the left of the plot. Here, this is the sound speed space where the phase transition is very vivid, that you had some smooth behavior and then particularly some interesting behavior that happened here. We suspect that this is what we can detect from these macroscopic kinks. And the presence of the local minimum corresponds to the endpoint of the phase transition. And then the onset density is chosen by finding the preceding maxima for any given onset densities if it passes a certain threshold. However, this assumes that every equation of state draw will have a local minima or in the feature space that was defined. And towards the end of the conclusions of the paper that was published last year, they acknowledged that this does not hold for certain equation of state models. And so, for example, something like this, we can see that there is some variation in the sound speed space, but it does not manifest as a local minimum in the feature space. And therefore, the model does not, or the algorithm does not perfectly detect the onset and the ending densities of the phase transitions. And therefore, my goal for this summer was to somehow modify the feature extraction algorithm or to come up with an alternate feature that can detect these cases as a whole. So the cases for which we don't observe minima in the feature space that was defined initially. And to do that, what I did was I picked one of the cases that was failing. So particularly one equation of state draw from something called the Gibbs equation, the Gibbs equation of state family. And what I tried to do was I tried to vary some property of the curve to see if I could control how a feature appeared or disappeared in the feature space. And I noticed that as I varied the amplitude of the Gaussian and the extent to which the phase transition was drastic in the sound speed space, it appeared that the curvature in the arctan D curve also decreased. And to me, this motivated that there is some information encoded in that curvature. It just does not manifest as a strong minimum in all cases. And for example, what I'm trying to exactly say is more explained by this small animation that I made. So you can see that as I vary the amplitude, you can control the curvature such that it nearly becomes undetectable. And for all of these cases, the model is just trying to detect these other local minima. And for this, what I had in mind was that rather than encoding it as strict extrema, what we should do is come up with a feature that can encode curvature in a more subtle way. And to do that, what I did was use the intuition of fitting circles to part of curves. And the way that is done is by measuring the radius of curvature at every point, given that we interpolate our curve really well. And I defined Kp, which was a new feature as a signed curvature of the arctan M curve, parameterized by central pressure. And the main idea is that when the curve bends very suddenly and changes direction, the idea is that you will observe distinct peaks or extrema in this new feature that I've defined because the radius of curvature decreases, so the curvature increases. And this seemed to encode more subtle information about the curvature of arctan D than local minima, which was proposed earlier. And this seems to identify previously undetected phase transitions as well, as I'll now show in a series of plots. So everything that I'm now showing is implemented with this new feature rather than local minima that was proposed earlier. For example, this first case is where we have a vivid local minimum. So we tested on cases where the previous algorithm already worked to see if it's abstract enough. And we see on the top left that this is the feature space. We see that there's a very vivid local minimum. And intuitively on the right, we have the new feature space where the green and the red show the anti-clockwise and clockwise directions. So based on the sign of the curvature. And we see that we start off with a reasonably clockwise rotation in the curve. Momentarily, we flip sign, we enter the anti-clockwise regime, we peak because there's a very sharp change in curvature, and then we resume the clockwise rotation again. So the way I'm picking information from this new feature space is that I find noticeable local maxima such that the sign curvature is positive. And this seems to be a better proxy for the endpoint than local minima, as well as we'll see later, like shortly. And you can see here in the sound speed space that this is exactly the point where the endpoint occurs, and then we can sort of trace back and find the onset densities as well. And even in the more macroscopic relations, which is where the map is coming from, we can see that there's some behavior that causes these more macroscopic properties to change as well. And other, like for example, this part also shows a similar trend because there's a local minimum, so similar behavior, there's a peak, but of a lesser magnitude because the curvature is decreasing, and this is all tested on the models that were constructed earlier. The same case holds here as well. Same, not particularly interesting in the sense that this has a local minimum, so this does not yet have an advantage of the old implementation. But now, as I decrease the curvature to a greater extent, so something like this, while there is a local minimum, it seems like a point before the local minimum is where the true information lies. So in the feature space, you can see these two curves which occur because you suddenly change direction when you come here. There's a small kink that occurs before the local minimum, and that seems to be a better proxy in the feature space. So for example, this one arrow, leftward arrow, corresponds to this. Sorry, what?
Have 1 minute.
I can't hear you, sorry.
You have 1 minute.
I have 1 minute. Okay, yeah. So this is basically what we see for these local minima cases. And what's more important are these cases where there is no local minimum, but it detects this kink that we have. And what this is a result that would have failed with the previous implementation. And this is one result that would have clearly failed with the previous implementation because you don't have a minimum to detect at all. The current limitation is that if the sign does not flip, then we don't detect a phase transition. However, there is certain information that we can sort of extract from these, from the feature space, but those are certain steps that have yet to be explored. So the conclusion is that the new feature implementation that I'm suggesting here seems to detect phase transitions that are previously undetected. And in many cases, they can also identify onset densities. However, I need to verify that claim yet. And so an implementation that combines both the old and the new one seems to work for all US realizations. And this is particularly powerful because we only have macroscopic relations. And in the next steps, I'm going to implement the same feature on more simpler spaces rather than the arc and the M curve. Thank you. And I am very grateful to my supervisor for guiding me throughout this entire project. And I am now open to questions.
Nice. Thank you for the nice presentation. Do you have any questions? Well, I have one. You were talking about the ARC10 helping with your modeling. I was wondering if it helps you to propose any basically shape that you think as the intuition may help you, and then use a machine learning package. There's some available nowadays that basically come up with an analytical fit that reproduces exactly the behavior that you want for that specific behavior. Would that be something that helps you?
I'm sorry, can you come again? I couldn't hear you clearly.
Okay, so it's possible to basically draw any line that you want, that you think will help with exactly the behavior that you expect, and then use a ML package to tell you what analytical form gives you exactly that. Would that help you?
So yes, that is quite true. It would help me because that is precisely what we've been doing. We've been constructing equation of state models however we wish, because the only constraint on a physically possible equation of state model is that has to be monotonically increasing, because the derivative of that is the sound speed, which has to be real. So yes, that is exactly what I've been using in construction of the equation of state models. I'm varying it however I want to see how it maps. And that is what helped me identify the trend in the first place. Does that answer your question?
I'm saying that you can also use an ML package to give you the analytical form of something you come up with. If you just want to draw something you don't know what it corresponds to, you can use an ML package to tell you that this is a combination of arctangent, whatever, put together in a special form.
Yeah, that seems like a good idea, which I could use in the future. I haven't looked into that yet, but I could definitely use that to test the robustness of the algorithm itself.
Cool. Any other questions? No? Okay. Gotcha. So next we'll hear from Mateo. I think yeah. Do you want to use your own laptop or use this text slide? Actually, yeah, okay, perfect. So we can go up to you. That would be great. Here, this is right. Oh yeah. Okay. And you have 10 minutes, and I won't shout because you're in the room.
Okay.
I just raise my hand when you have like 1 minute.
Slide just here.
No, here.
Okay. So, hi, my name is Mateus. I'm a student at University of Toronto, Mississauga, going to fourth year. And today I'm going to talk about my project, which was supervised by Jennifer. And it is probing the cosmos with 21 cm, the spectral imprints of ionization cavities. And here in this image, we have a figure showing the morphology of the epoch of ionization. These are the structures that I'm going to be focusing on this talk today, and I'll be referring to them as ionization cavities or ionization bubbles. So here, I just have a simple diagram showing the cosmic evolution time. Over there, we have the Big Bang and the CMB. And how we observe so far back in time is we use the 21 cm line, which is emitted when there's a spin flip in the electron of the neutral hydrogen. So here in this region is where the focus of the project is. As the first stars and galaxies start to form, they start to emit radiation, and that radiation has a higher energy than 27.2 eV and start to ionize the surrounding gas. And as it started to ionize, which was previously mostly neutral gas, started to form these regions of mostly ionized gas, which I've referred to as ionized cavities or bubbles. And since the 21 cm signal is emitted by neutral hydrogen, those ionized cavities leave an imprint on the signal that we observe here at redshift Q. So here I have this video showing over here we have the morphology of the epoch of ionization, and here we have the ionization energy. And this is simulation, a large hydrogen simulation, which is the PSIN simulation, the state-of-the-art epoch of ionization simulation. And what I have here is I isolated one of those structures by using the ionization fraction to define the boundary and using the temperature profile along each Cartesian direction to define the center. And this is only one way to define a bubble. There are multiple ways that we could maybe define and isolate a bubble. But this is just to show what a ionization cavity could look like. And how can we infer the properties from the 21 signal traveling along this bubble? Well, we can use the observable right here, which depends on the line intensity and continuum intensity, and this is just Rayleigh's approximation, converting from specific intensity units to temperature units. And here, the specific intensity and the continuum intensity we obtain then by computing those two radiative transfer equations. And since we're transferring the radiation across a large cosmological scale, we differentiate over redshift. And here it's important that we use the invariant intensity, which is just a regular line intensity, continuum intensity over nu cubed. And this is just to keep things neat and constant as we travel through redshift. So here, as I previously mentioned, we are transferring the radiation across redshift space, but as we do that, we're also transferring the radiation across frequency space because they're both linked. So as we travel down in redshift, the frequency is shifted because of cosmological expansion or cosmic expansion. But there are also, and this is a global process, but there are also local processes that causes a frequency shift, such as a Doppler shift due to the motion of the neutral gas. There are also processes related to the line broadening. For example, the cosmic expansion also causes a compression of the line web.
Sorry to interrupt you.
Yeah.
The slides are not being shared online.
Oh, okay.
Sorry about that.
That was. Should this going?
Yeah.
Okay. There are also local processes that contribute to line broadening. Here's the line profile, and it is mostly defined by the gas temperature and the turbulence velocity. So this is just to show that your frequency space, your configuration space, and your redshift space, they're all entangled. So this is the current method. It is derived from the line radius transfer equation, but to derive this and to make the computation easier, there are a bunch of assumptions. Are made, and one of those assumptions is that we can establish a one-to-one connection between the observed frequency and the redshift that is emitted. So, yeah, and also it assumes that there is no line and continuum interaction. So to better observe this, what I've done is I constructed several toy models to compute the linear transfer across a reionization cavity. So here we have a very simple model at local reference frame redshift 0, and here we have an ionized region, and here a neutral region, and I'm computing the line continuum radiative transfer across this light rate. So here in this plot, we have the line intensity across the path length of the light rate using the line radiative transfer equation. And here I have the same one, the same temperature brightness across path length using the optical path method. And here, as at a redshift 0, because things are neat and simple, we don't see much of a difference between the two methods. And now instead of only using one ray, I'm using 5 rays traveling through that bubble. Here we have the point at which the rays intercept the bubble, and here we have the spectrum computed from those rays. And again, this is a standard sphere, but if we have an expanding sphere, then we need to consider the fact that the speed of light is finite. And here we have, this legend is showing different moments in time of the bubble expanding, and here would be the apparent shape considering this finite speed of light correction, because if photons are emitted at a different position, they will reach the observer at a different time. Here we have the effective path length of the light rate at the apparent shape, and here we have the computed spectrum as well. The only difference is the amplitude, because here, instead of considering the full 80 megaparsec bubble, we don't consider this region, so there's more emission cells that the light rate travels along. So after that, I placed the bubble at a different redshift. I verified the code using 2 redshift cells. So I computed the line rate transfer at two emission cells, which corresponds to those 2, and then I propagated them down from redshift 12 into redshift 0. And if we use the co-moving density, then that propagation follows 1 over nu cubed relation, and if we use the invariant density, it remains constant as we travel to redshift. And then instead of only using 2 cells and 1 ray, I computed the spectrum from all of the redshift cells in the simulation, and also computed the spectrum along 5 light rays. So here we have the standard bubble, the standard spherical bubble, and as we can see, the shape of the spectrum is symmetric around the 21 cm line, and here we have one considering the finite speed of light correction or expanding bubble. And as you can see, the spectrum is now asymmetric around the 21 cm line, and the width of the line is also compressed. And that frequency shift happens because as we consider the speed of light correction, the shape of the bubble is elongated along the line of sight, and the red shift at the center of the bubble gets shifted towards the end. And here, those are computed using the C21 LRT. And here we have the computation for that case using the optical depth parameterization. And now we can see the difference. As we compute the optical depth parameterization, the temperature brightness drops to 0 as soon as it reaches the bubble zone, and we lose information by using the standard method. So in summary, what I did this summer was I learned how to use the 21CM as a probe of cosmological ionization. I constructed various toy models of ionized cavities. I also verified the codes for signal computation at redshift 0 and a higher redshift. I assessed the conditions when the current methods computing the 21CM signal were valid or not. And I also extracted ionization cavities from the thesis simulation. So what is next is to incorporate additional toy models to investigate other effects, such as if two bubbles are overlapping or if there's a bulk motion of the ionized gas, and also use the code to compute the signal from using a Thiessen bubble or a Thiessen structure. So yeah, that's it.
Thanks for the nice presentation. I was wondering, did you model the edges of your bubbles as being perfectly sharp, or was there some transition region between fully ionized and
I consider the fact that of an intermediate region, but those plots were only a sharp cutoff between ionized and not ionized. Yes.
So when you want to do this on the simulation bubbles, do you plan to extract from the state where you did initially, or do you have like a plan of extracting from different places?
So I also tried extracting the bubble using different clustering algorithms, and that didn't work very well, so it's still something that we need to investigate.
So there are some new codes out there that are doing morphology mapping of star formation regions, like in the super bubbles in the galaxy. But the same codes have started to be used for other object identification. Would anything of that help?
Probably, maybe. Yeah, again, like the clustering algorithms that are used are very simple, like TensorFriends or K-means. So yeah, it's not something that we have investigated deeply yet, but yeah, potentially.
Other questions? Thank you so much. And we have a 10 minutes break. So if you can, walk around, stretch, get some water, and then we'll resume at 11:13 here. Internet. Yeah. Okay, so we have Anna Karina telling us about the summer project now.
Hi everyone, my name is Anna Molina Colina. I'm going into my last year at McMaster. I worked under the supervision of Joanna, and today I'll be talking about unveiling star formation in the Milky Way using 3D dust temperature. So just in case anyone doesn't know, interstellar dust are particles that originate from the death of stars. So they're made up of elements such as silicates and hydrocarbons. Dust is identified in two main ways, the first being extinction or reddening, which is caused by the absorption of light from the dust. The other is dust emission. And studying dust is very important for learning more about star formation, which is the focus of my talk today, as well as planet formation and cosmology. Stars are born in these large clouds of gas and dust, called giant molecular clouds, or GMCs. In these clouds, cold dust will clump up into these dense regions, and once the density is high enough, it will collapse into a star. These stars are called protostars, and then they become pre-main sequence stars. In this process, there will be regions of hot gas next to cold gas, because the cold gas is how these stars are born, but then these stars will start heating up the gas around it. Star formation can be identified using tracers of various kinds. For today, I'll be focused on young stellar objects, or YSOs, which are these very young stars. And the other one is star formation complexes, or SFCs. So these are large regions that contain many star formation regions, or SFRs. In this image, you can see an SFC, and all the SFRs are circled in red. For my project, I use data from my supervisor's 3D dust temperature map. This uses both dust reddening and emission data, so you can see the intensity of the dust as well as the temperature. So the reddening map shows the density of the dust, because the more dust there is, the more reddening you'll see. And then the temperature map shows the temperature of the whole sky, so this does contain information of regions that do not contain dust. These maps are separated into voxels, so that is made up of a superpixel and then distance slices, and each superpixel basically has a certain amount of pixels within that. Each voxel will have a specific temperature associated with it. What's really interesting about this dust map is that you can see these regions of cold gas, which is the yellow regions, next to the regions of hot gas, which is blue. And as I mentioned before, this is very characteristic of star formation. And in fact, you can actually associate it with known SFRs. And here you can see Orion A, Orion B, and the Orion ring. But as I point out in the purple circles, there are regions with these similar characteristics, but they're not associated with a known SFR. So that brings me to the goal of my project, which is to use this 3D map to create an algorithm that will identify known SFRs and then find new ones as well. This is important because we can find these new potential SFRs, and that's very exciting. We can investigate it with other methods after that. We can also resolve distance ambiguity. So that means that for any objects in the sky, like YSOs, that don't have a clear distance, we can find these in the map and then provide a possible distance. And lastly, we can learn more about the structure of SFRs. So we can find structures like bubbles or rings, and then learn more about these in the map. So the way that I did this was I first identified properties in known SFRs. So these include the star formation tracers that I mentioned, as well as temperature and density variation. I analyzed these properties and I found trends, and then I found potential SFRs that follow these same trends. So the first thing I did was I compiled a list of YSOs and SFCs from various catalogs. I also found local molecular clouds, or LMCs, and these are associated with known SFRs. And the other thing to note is the purple stars, those are KYSOs. So they're YSOs associated with known SFRs, so I use these the most in my analysis. What I did with these KYSOs first is I plotted them over the reddening map. And the reddening map is very useful because you can visually see the dust distribution. And this shows both the Orion and the Perseus LMCs. And you can see that the YSOs fall where the dust is, which is what we would want. The next thing I did was I started flagging properties of these known SFRs, and this one shows high density or high reddening areas. And you can see I flagged it correctly because they're exactly where the map shows that there's high density. I did a similar method for temperature, but temperature is a bit more complicated because I only wanted to analyze the regions that have dust. So we decided that the best way to do this is to first associate each temperature with an RGB channel. You can see in this Gaussian here sort of how I did it. I then combined this channel information with the reddening map to only get the regions with dust. And I was able to create RGB images of parts of the sky, and you can see one for Orion right here. You can clearly see what are the hot and cold regions that I would want to look at. To get a closer look, I made this panel, and the first two show Orion A in the blue color and then Orion A in the red color, and you can clearly see which parts are brighter in which color channel. With this, I flagged what is considered hot and what is considered cold. You can see this here over the temperature map and over here over the reddening map. Then I looked at which hot and cold regions are within 5 parsecs of one another, and I defined this as a neighboring hot and cold region, and this is this result here. And as I mentioned already, this is very characteristic of star formation, so this is arguably my most important flag that I made. And I put this RGB image here as well so that you can see whether or not the hot and cold regions match this image, which they do pretty well. Because of the importance of these neighboring hot and cold regions, I wanted to investigate them further. And how I did this is I looked at them in the reddening map. And you can see some examples that I found of these very interesting features in the reddening map, and there are a lot of hot and cold regions there. These could be potential new SFRs, or they could be features in the sky that I haven't identified what they are yet. But in order to trust these results, I wanted to know how well these hot and cold regions can be as tracers for star formation. So I correlated them with the KYSOs. Here I show the KYSOs for Orion A and Orion B, and they correlate very well with where the YSOs are, and as I mentioned before, where the temperature is. Here is the same result for Perseus. The hot and cold regions are very close to where the YSOs are. I also showed density, but for the most part, I looked at hot and cold regions. I wanted to quantify these results, so I actually calculated the distance of the YSOs to the closest hot and cold region. So I did this for all the YSOs in the sky within 200 parsecs of a hot and cold region, and then for Orion and Perseus on their own. And what we noticed is that the majority of the YSOs will have a hot and cold region within 100 parsecs, and you can see these very clear peaks. So we made an argument that an SFR will have a hot and cold region within 100 parsecs. With that argument, we decided to make a definition for a hot and cold region, for a potential new SFR, and those were hot and cold regions that have no KYSOs within 100 parsecs, because this could mean that that area hasn't been studied well because there's no KYSOs near it. Here is the positions of those regions as well as their distance, but there is still a lot of investigation to be done on these, such as visualizing where they are. The other application of my result was I used it to resolve the distance ambiguity of the YSOs in my catalogs that had no distances. So what I did is I tried several distances, and whichever distance had the closest hot and cold region, I presented that as the most probable distance for that YSO. Here is the red shows my inferred distances, and then the blue shows what the YSOs in the catalogs that have distances are. This image on the right shows the same image, but it points out which catalogs are which. You can see that my data sort of matches what the data in the catalogs looks like, but I do need to evaluate the accuracy of this method. Some other analysis I did was I created RGB images for those features that I showed in the reddening map that had a lot of hot and cold regions. I also looked at the SFCs that had ambiguous distances, but there was a bias for the closer distances since the further ones have less hot and cold regions there. So the results are a little bit skewed there. And the last thing I did was I calculated the distance of YSOs and SFCs to some of the other properties that I looked at. In conclusion, I was able to identify properties of known SFRs, and I used these properties to make a list of potential features of interest. I was able to conclude that neighboring hot and cold regions do act as good tracers for star formation because the majority of YSOs will have one within 100 parsecs. I flagged potential new SFRs, and finally I found potential distance candidates for YSOs that previously didn't have distances. In the future, I would like to use a greater resolution map. I'd also like to investigate those features with the hot and cold regions further. So I would like to correlate it with the YSOs or correlate it with other objects in the sky, such as PMCs. I'd like to evaluate the accuracy of my method to get the distance candidates. And finally, I'd like to look at those bubbles and structures in the dust map. Thank you everyone for listening.
That was a really nice talk. When you were identifying the hot and cold regions, I think you mentioned that you neighbor together those that are within 5 parsecs.
This one, right?
Yeah, quite far.
That is just what I considered like the closest. If I did anything greater, it would kind of cover, there would be a lot of points. Like, I don't think that, you see this red point over here? That isn't very close to this white point, but with 10 parsecs, it would show up as close. So I felt like 5 parsecs was a good distance that wasn't too far and not too close.
Are there any other questions? Yeah.
So what's the temperature for the hot and cold region?
Yes, so I use anything, I use a Gaussian. So what I considered hot, I think, was anything above 0.8 here of intensity, and then anything of 0.8 in red. So that was about, you can see there's like below 10 Kelvin and above like, I think about 25 Kelvin. Yeah.
Other questions? Okay, thank you so much. Oh, okay, there's a slide.
I mean, I just put their slides in order.
Okay.
Various times.
Okay, so next we have Ben.
Okay, perfect, thank you. Just this keyboard here?
Yeah.
Okay, hi, I'm Ben. I spent my summer working on parameter estimation of black hole neutron star binaries, populations using gravitational waves, and I was supervised by me. Okay, the merger of compact objects emits gravitational waves, which were first observed in 2015 by LIGO. Since then, there's been 90 publicly released events, where an event is a neutron star merger, or binary neutron star merger, binary black hole merger, or a neutron star black hole merger. And currently, there is another observational run going on where even more events are being detected. And up till today, there's around 4 neutron star black hole binary mergers been detected. That number kind of fluctuates because it's sometimes hard to tell which are neutron star black hole mergers and which are binary black hole mergers due to uncertainties in the masses. So the aim of my presentation is to estimate parameters of Mach population of neutron star black hole binaries using simulated gravitational wave signals. We're doing this to help determine how many neutron star black hole mergers need to be detected for questions around their populations to be answered. Example of these questions are how many detections are needed for the black hole spin measurements from neutron star black hole binaries to be competitive with the measurements from black hole binaries, which in turn that question can help answer how well can we constrain astrophysical scenarios about the formation of neutron star black hole binaries. So why neutron star black hole binaries in particular? The point that we're focusing on the most is the fact that black holes, the spin of black holes in mergers for neutron star black hole binaries are much better constrained than in black hole binaries. This is because gravitational wave signals can measure chi effective really well, which if you have a large difference in masses, where mass 1 is, or if the primary mass, which is M1, is much bigger than the secondary mass, which is M2, then chi effective is essentially just chi 1. So then you can constrain the spin of the black hole very well. Another point is that large asymmetries in the mass ratios allow for higher order multiple moments of the waves to be detected, which then rely on different properties and will break degeneracies, because gravitational waves are quadrupoles, and the dominant node is 2,2. But if you have larger asymmetries, then the subdominant nodes start popping up, and then you can kind of detect those too, and each of those depends on a few parameters primarily. So if you get the other nodes that come out in the signal, you can break the degeneracies that are found just in the dominant node. One of the drawback of using neutron star black hole binaries is that their parameter estimation is a longer runtime than black hole binaries. But we employed relative binning to combat this, where relative binning, you assume that neighboring waveforms in parameter space are not that different. So if their ratio can be approximated as linear, so you don't have to calculate the waveform at every single point in parameter space, you can just calculate a few and kind of interpolate in between them. For a single event parameter estimation, so for one merger, your neutron star black hole mergers are described by 16 parameters that can be found within the gravitational wave signal. These, you can construct a waveform based on these parameters and inject it into a noise stream from a detector, and then attempt to retrieve that signal using Monte Carlo schemes, which using Bayesian inference to calculate the probabilities. So on the bottom left, we have the probability where the L is the likelihood, pi is prior, then the Z is the marginal likelihood, and then your likelihood or your log likelihood, which you have to use so you don't run into overflow errors, depends on Sn, which is the power spectral density, H, which is your signal you either injected or are observing, and then mu, which is the signal you're varying using Monte Carlo to try to kind of narrow down the parameters that you want. Once you've done that for a population, you can estimate the parameters of the population as a whole using a hierarchical Bayesian inference. To find the hyperparameters, which are what go into your kind of population as a whole. So I use models for mass, spin, and distance, and then made a population out of that. And then once you get the posteriors out of your individual events that you run parameter estimation on all, you can run parameter estimation for the hyperparameters, also using Bayesian inference, using the multiplied probability of all your models. And then you can kind of work your way back up the chain to get the parameters of the model you originally created. Then for the models I used, for the primary mass, I used so I read a paper for that synthesis, or like a population synthesis paper specifically for making neutron star black hole binaries. And I fit their resulting primary mass distribution with a couple of Gaussians just to have a close approximation to what their end result looked like. And then for the secondary mass, I fit a really tight Gaussian to kind of 1.7 solar masses. This is because relative binning does not handle really small mass ratios well. So if below 0.1, our approximation of it being linear kind of falls apart. So I restrained it so that mass 1 couldn't be more than 10 times bigger than mass 2. The spin population, I tried to kind of mimic a couple subpopulations. So when, in kind of your typical isolated binary channel, when the first compact object collapses, it can spin up the second compact object, which usually the heaviest one collapses first. But there are some mass ratio reversal scenarios where the lighter object can collapse first. And then so you can get spins or primary spins that are centered at 0 or higher up. So to kind of make a simple model that I could retrieve the parameters from when I run my estimation, I centered one at 0 and centered another Gaussian at 0.5 to kind of get this two different subpopulations. And then secondary spin of the neutron star, I held at 0, which is just for simplicity, and most neutron stars are spinning not very quickly in these scenarios anyways, and also for the same reason that you can get chi1 very well, you're going to have a hard time recovering chi2 because the mass is, again, so much smaller than primary mass, so you're never going to really be able to recover it anyways in these sort of runs.
Do we need to allow James?
All right, and then for the distance model, I kind of used their typical compact object merger distance model. It's tied to star formation rate, so I used just the local one because you can't observe neutron star black holes mergers from that far away because their mass is not that high, so just 2.7. is tied to the local merger rate, so I just use that. And then in the denominator, you need another factor because merger rate is uniform in volume time product. So a kind of whole step-by-step process. You can draw events using detector strain and noise from distribution models that I showed, using all of these codes, which we created. And then you can run individual parameter estimation. I use the program BillyPipe on the cluster. And then using the posteriors from the individual events, you can run hyperparameter estimation and try to get your original model attributes out. So this is an example of individual parameter estimation. You can see things are pretty well constrained, and I kind of got out what I put into them. And so I have mass ratio, chirp mass, then primary spin. Chirp mass is just kind of the mass parameter that you can get the best from gravitational waves. And it's just a combination of primary mass and secondary mass. Then this is an example of kind of 20 events as a population, and then trying to get what I put out into them. This does not look very good because I have not accounted for selection effects yet. I had a little trouble implementing that. So as you can see, this is supposed to be like 2.7. This is the distance parameter. But it obviously favors its bias towards values that are much closer because it's not accounting for the fact that the closer ones are much easier to detect than further away ones. The slides are a little mixed up, but this is supposed to be what I'm doing next. So the first thing to do is my individual parameter estimation that I showed earlier. I'm not injecting the signal directly, or the noise, the strain and the noise directly from the sampling code like I wanted to. For whatever reason, it's just not recovering those values very well. So instead, I injected the parameters of the events themselves into Bilby and then create a new waveform, which roughly works, but it's not the exact same. So the SNR threshold that you cut using the sampler isn't, it's not quite as rigid as I'd like it to be. And then next step after that, can I have like a minute?
You're almost back.
Okay, well.
Yeah, just wrap up.
Yeah, then the next thing I'd like to fix is obviously implement the selection effects into the hyperparameter estimation. Then after that, I'd like to change waveforms because I'm using one that doesn't allow for processing spin yet. So we can implement that and make the program more general. And then the last step is you can vary the amount of object or mergers in your population to see how that affects your hyperparameter posteriors. Thank you.
Just a quick question. So you mentioned this technical limitation about the relative binning, where you can only go down to like a 10-to-1 mass ratio or something.
Yeah.
So that definitely puts a lower bound on your neutron star mass distribution. Have you considered, though, sort of expanding the distribution to be wider up to higher masses to simulate, maybe you think in nature that there may be a broader range of neutron star masses?
Yes, that is also something I could implement in the future. Because we weren't sure whether to kind of treat the primary and secondary masses separately and try to pull back the parameters from each model separately, or kind of combine them and account for mass ratio parameter estimation. So you could definitely go higher. I knew DT wasn't too fond of the idea because he likes kind of cluster stuff where the neutron star mass is usually a bit lower. But you could widen that all the way up and then kind of have a bigger Gaussian to sample from.
Anyone else? Well, when I stop, I was wondering in your posteriors, on the orange, the fiducial values were trying to recover, like the lines.
Yeah.
Some of them had a bit of an offset. Do you think that's because
In this one or the other?
the previous one? These guys, yeah. So like the third one, for example.
Yes. It's kind of.
Well, That's okay, that's normal, like it happens all the time.
Yeah.
Like, I was just wondering, do you think it's because there's a degeneracy over there, or?
Could be. Yeah, it's one of those things where distance is one of the ones where I've had a harder time nailing down exactly. And you can see like distance and chirp mass are closely related in the signal. So if you don't nail that down, you're not going to nail distance down. So you can see it's a little bit off in chirp mass, and now I'll move over to distance too. So yeah, it's kind of, they're all closely related. So if you don't get them all, there'll be quite a few that don't line up. Does that make sense?
Anyone else?
These ones are showing, are they injected into noise or zero noise? Just
Into noise.
Into noise, yeah. So that could be another reason why also
Yeah.
the injection is perfectly recovered.
Okay, thank you so much. So next we have Nick. Yeah.
Thank you. Hello, my name's Nick. I'm going into my third year at the University of Calgary. I was supervised this summer by Joanna, and my project is measuring the morphology of the galactic magnetic field in 3D. So the main goals of the summer project were to expand on her 3D dust temperature map that Anna showed a few minutes ago. And my job with that was to incorporate polarization data to try and model the emission in a way that we could recover some information about the magnetic field. Why is this important? Magnetic fields have strong implications regarding star formation, galaxy formation, and cosmological measurements. And the large-scale structure of the galactic magnetic field is not very well understood. So this could be a new method of trying to probe it and see if we can cover some information there. The main idea is that interstellar dust grains are elongated, and they can align with the magnetic field in a way that they can emit polarized emission. And so we want to try and model that emission and backtrack and see if we can recover the information about the magnetic field. So for this, we use two data sets, the first of which is the dust density map that Anna mentioned. And so that is created by using parallax measurements from the Gaia telescope to find the distances to stars, and then stellar photometry from the pan-stars and two mass surveys to measure how much they were reddened along the line of sight. And you combine those and you get a 3D dust temperature map. And the other data set we used was dust emission maps. So we used the Planck Space Telescope and the IRAS-Turbay Space Telescope. For this, we used the 217, 353, 545, and 857 gigahertz maps from Planck, and the 100 micron map is from IRAS-Turbay. And the Planck telescope also measured the polarized intensity of light between 100 and 353 gigahertz. We used the 143, 217, and 353 gigahertz maps. We chose these frequencies because they're dust dominated. So as you can see, if you go down to lower frequencies, you start to get, this is the intensity map, synchrotron and spinning dust and CMB mixed up into the signal. So we cut it off at 217 where it's still dust dominated. And then you see in polarization, a lot of those sources aren't highly polarized at the lower frequency. So we're able to push that back to the 143 gigahertz map for the polarization data. So the previous work, as we saw, Anna showed the video, so I won't show it again, but it's the 3D dust temperature map, which models the dust as a modified black body and fits this rho parameter, which is a conversion factor between optical depth and the dust density, the spectral index of the black body, and the temperature of the dust. So these are my gross emission equations. This is the original one that was used for the dust temperature map. And then, so that's modified black body. And then for the Q and U Stokes parameters model, we keep that modified black body, but then add a couple terms here. The psi term describes the orientation of the polarization on the sky. The alpha term describes the orientation of the dust grain relative to the line of sight, and that tells you about the magnetic field, and then also a fractional polarization parameter as well. So to fit these parameters to the data, we use what we call superpixels and supervoxels. And so a superpixel is a 2D big pixel that you just place on top of the emission and reddening data. And we do that so that there's more data within a superpixel, and that can help to constrain the parameters when you try and fit them. And then a supervoxel is just a three-dimensional stack of superpixels along the line of sight. And so what we did here is we took the dust density at different distance slices and then modeled them as the black body and scaled the emission with the dust density at that distance slice so that when you sum over it, you try and recover the emission maps. So this is just a little equation showing how we did that and summing over the different distance slices along the line of sight. This is for the dust temperature map, and then this is with my new QNU data sets and the added parameters. And then this is the function that was used in the dust temperature map initially to quantify the likelihood of the parameters that we fit to the data. And it gets a little bit longer when you add the new data sets and the new parameters and all that. So there are some limitations to the data sets that we used, namely with the dust density map. There's a pretty big hole here. So that's because the stellar photometry is done with the Pan-STARRS telescope, which is in Hawaii, and so this region is below negative 30 degrees of declination, so not visible there, so we just leave this blank. And then also within this map, this shows the maximum reliable distance of the dust temperature map. So you can see that within the galactic plane, that distance is a little shorter. That's because there's so much dust there that the stars just get completely extincted a little earlier, and you can't measure the dust beyond a few parsecs. And then up towards the top and bottom of the map, there's just not enough stars, and same kind of problem occurs. But then up below and above the galactic plane, you're kind of in a Goldilocks zone there. Then there's also some distance resolution limitations. So the density map is decomposed into 120 distance slices, and they're logarithmically spaced between 63 parsecs and 63 kiloparsecs away. So as you try and use further away distance slices, you get pretty chunky data there. And then within the emission equations that we fit, there are some degeneracies. So that's why when you look back to the dust temperature map, the dust temperature is in 3D, but then the spectral index and the conversion factor, those are 2D, because if you let them all vary along the line of sight, there's multiple different solutions you can get. And so we haven't really had time to look into if that's the case with the new polarization parameters. But the code is designed in such a way that any of the parameters can either be fixed in 2D, or they can be fit along the line of sight at each distance slice, or they can be not fit for it all and just set to a constant predefined value. So if that does end up being the case that there's any degeneracies, it should be able to handle those pretty easily. So the results are that it runs. So we can optimize for all the parameters there. We haven't really had time to look into the analysis of the output to see what configuration works best in terms of, here we have the alpha parameter floating along the line of sight, but we keep fractional polarization and the psi parameter constant. Those can obviously vary as well, but we just haven't had time to look into which work best. And you can see here that it does recover the initial intensity and polarization maps and reduces the residuals down to kind of noise levels. There are a couple problems that we noticed kind of right at the end there. Namely that the fractional polarization map does not perfectly really get recreated. And so about that, we noticed that there, within our data sets that we have from Planck, there seems to be a frequency dependence of the fractional polarization. We're not too sure what to do about that. Our fractional polarization we have in the model is not frequency dependent. So that's just something to look into for the future, but no real steps there as of now. Future work, definitely investigate the degeneracies, see what different configurations show and which ones work the best. That's all pretty much set up, so if we had a bit more time, I think we definitely could have figured that out, but hopefully it shouldn't be too long. And also maybe see if there are pre-existing models of the galactic magnetic field and see if those align with what the code outputs. And that's about it.
Do you have any question?
All the bases.
So what did you find to be the hardest part and the easiest part of your project?
Well, I would say that the hardest part, I've written plenty of codes before, but never any that have to be used again or read by anybody that's not me a week from whenever I wrote it. So this is all, I made some moderately significant changes to Ioana's repository to add all this stuff. And then inevitably there were infinite bugs and nothing worked. And then over the course of many months, kind of slimmed those down and tried to get it back down to something that's readable. So that was a big learning process. But I'd say that was probably it, is trying to make it readable. I'll do some work on that tomorrow for documentation. But yeah, trying to make it efficient as well. There's a lot to optimize here. And there were times I'd run a little sample and say, if I do the whole sky, it would take 2 years. And then that took me a month to get out of that little hole. But now it's not that long.
Cool. Any other questions?
Do you like explaining about the fractional polarization? What's the highest value and why we should expect a frequency dependence?
I don't know why we should expect a frequency dependence. We initially did not expect a frequency dependence. And so in our, so in our equations that we use, we just have it as a fixed kind of scaling factor for the polarized intensity. We've read some papers and it looks like this is a Planck paper here. It looks like 20% is kind of the highest, or the upper limit of what you would expect in some regions. We largely recover that, like most of our data falls within there. We do have, of course, a decent amount of data well beyond that, but I've mapped that out, and a lot of that lies up here and down here in regions where the dust density map isn't very accurate, so those numbers are, not necessarily to be trusted right away. But yeah, it seems like from the Planck papers where we got the data, 20% is kind of the upper limit of what you'd expect.
So what's the frequency dependence shown from Planck? I suggest
I don't know. I kind of just made these plots yesterday when we were looking into this, not recreating the map that we really expected. So these are the fractional polarizations that we see, and they maintain the same structures, but as you can see, they don't really produce the same values.
So this is the data itself. This is just from the data. So there's wondering that it's like, okay, what's going on there?
Yeah, we don't really know what to do about this. That's something to figure out for sure. It's on the list.
Okay,
all right.
Thank you so much. Are you here? Oh, you're here. Sorry. Great. Perfect. Yeah, so we have such blood. We're close. I'm sorry. I said it wrong. Okay, so 1 more 3 minutes.
Hello everyone, my name is Shashwat, and this summer I was working with Dr. Beatty and Proper Perda on studying the diffusion-free dynamo. I'm excited to share some of the results with you guys. To start, let's discuss magnetic fields. Magnetic fields are found everywhere within our universe. They're found on Earth, within stars, around black holes, and even within distant galaxies. Magnetic fields were first initially formed during the Big Bang, but any fields formed back then should have all decayed away by now. So why do we still observe magnetic fields today? And one leading theory behind that is the MHD dynamo effect. This essentially entails the creation of magnetic fields due to turbulent motions of electrically conductive fluids, such as plasmas. The MHD dynamo is governed by the MHD equations, and the two most important of which are the momentum and induction equations. So what the momentum equation helps us describe is how the velocities in the plasma are affected by pressure gradients, Lorentz force interactions, and external driving forces. And then using those velocities, the induction equation tells us how the magnetic fields evolve. Using these two equations, we can identify a few key phases of the dynamo. The first is the kinematic phase, and this is where most of the magnetic field growth happens. At this stage, magnetic fields are weak enough to the point where the energy grows exponentially in time. And if you look on a plot here on the right with the magnetic energy as a function of time, you can see here in the solid black line the period in which the kinematic phase is active. So as the dynamo evolves, the magnetic field gets stronger. And we reach the next phase, which is called the nonlinear phase. And at this point in the dynamo, the back reaction due to the Lorentz force becomes important. And what happens here is that it slows the growth down from becoming exponential to linear in time. And if you look here on the same plot, except now plotted on a linear scale, you can see in the dashed line where the nonlinear phase occurs. And finally, the magnetic fields get so large, we enter the saturated phase. And at this phase, the growth is actually suppressed by resistive decay. And we can see that eventually the growth of magnetic energy becomes zero. And that is represented by the dotted lines here. But it turns out there's also another very important phase that happens early on. This is the diffusion-free phase. It is extremely brief, and you can only see it on very short timescales. And this happens before the kinematic phase. One key aspect of this phase is that the growth rate is much, much larger than what we observe in the kinematic phase. So for example, if you look at a neutron star merger simulation of the energy versus time, in this phase, you can see a period of really, really fast growth that is much larger than the growth that we see in the phase there. So that is the diffusion-free phase. And in 2002, Shikosha actually put forth a model of the magnetic energy spectrum, which helps us look at on what scales energy is distributed. And it predicts three things. One is that the integral magnetic energy should increase exponentially. The second is that the peak of the magnetic spectrum should also increase exponentially. And third, the width also increases exponentially. So there's a lot of inherent exponential growth in this phase. And what my goal of the project is to look at MHD simulations and see whether these predictions held true. So to better understand what power spectra actually tells us, it's first important to note that when we graph power spectrum, they're represented in terms of the variable k. What k is that it has units of 1 over length, and it helps us describe certain scales. So large k values represent small scale structures, and small k values represent large scale structures. So imagine if you have plasma in a box, and we're mixing it on some scales roughly the size of the box. We expect to see creation of kinetic energy at low k values. And as you mix for longer and longer, you expect to see some turbulence within the plasma. And what that turbulence acts to do is transfer the kinetic energy to smaller scales. But this transfer of energy cannot happen forever, because what happens is the viscosity acts to kill that transfer. Once this full kinetic spectrum is developed, we then start to see the development of the magnetic energy. the magnetic energy starts at some value, and what happens is throughout time it evolves in some sort of fashion which that model tries to predict. We expect to see some sort of peak growing to larger scales. We expect to see the width increasing. So this is what the model is trying to encapsulate, and using MHD simulations, we can try to observe this. So what we did is we used the flash code to solve the compressible MHD equations with some sort of turbulent forcing. And what we did is we chose a solenoidal driving function. So that's just like circular mixing on scales at k equals 2. So if you have a box of length L, k equals 2 would correspond to mixing on length scales of L over 2. We decided to fully develop the turbulence as an initial condition. This is not usually what people do in these simulations. Another thing we wanted to do was define these plasma parameters, the kinetic Reynolds numbers and the Prandtl numbers. And what those two numbers tells us is on what scales the viscosity and the resistance act on. And the PM number is a direct indication of how apart those scales are. The reason why we want sort of large PM simulations is because we want the most growth of the magnetic field. And finally, we defined an initial magnetic spectrum roughly at the k equals 2 mode, and we had it at that k to the 3/2 spectrum there, and gave it some sort of decaying features at the end. So once we had the simulation run, the first thing we looked at is what the integral energies look like. And as you can see here, as just basically energy as a function of time, we see the three familiar phases, kinematic, the non-linear, and the saturated. But if we zoom in right at the beginning there, we do see another phase that has much larger growth, roughly 5 times as much. And that was the diffusion-free phase. So another thing we were interested in is looking at the growth rates. To find the growth rates, one thing that we did is we took that Shikoshikin's model and fit it directly to the power spectra that we had. What we found is that the growth rate was actually decreasing, which is kind of interesting because when we looked at the growth rate during the diffusion-free phase from the energies, it looked like the growth rate was constant. That's something we'll get into a little bit later. Another thing we looked at was how the peak scale evolved. So this is actually what the power spectrum of the kinetic and magnetic energies look like. The kinetic spectrum was roughly constant, but you can see the magnetic spectrum, we had sort of the initial condition there, and then as time progressed, it evolved. So if you find the peak of that and plot it as a function of time, you can see that there's roughly an exponential behavior to its growth, but there is some sort of deviation, which was not expected. The second thing was measuring the width of the spectrum, which we sort of computed as shown. It was kind of like an RMS value of the spectrum, and also plotting that as a function of time, there is some sort of exponential growth there, but it also deviates. One main reason for this deviation that we thought was how dissipation acts within the plasma. Dissipation essentially turns the diffusion-free phase into having behavior more similar to the kinematic phase. And what we saw here is if we plot probability distribution functions of the dissipation term, you can see that during the diffusion-free phase, it increases roughly 2 orders of magnitude, which means dissipation becomes really important really fast within our simulations. And that could be one reason why we have such differing behaviors or expected behaviors of the peak, the RMS, and the growth values itself. But that doesn't really explain why the growth in the diffusion-free phase is generally larger than in the kinematic phase. And one way we can sort of look at it is this thing called the stretching tensor. And what the stretching tensor does is it transforms a certain volume element within our plasma. So if you can imagine some volume element with fields, then this matrix would essentially transform that along a stretching direction by some eigenvalue lambda s. So if you want extremely large magnetic field growth, it might make sense that you might have large stretching eigenvalues. But that's what we looked into. It turns out that the stretching eigenvalues during both the diffusion-free and the kinematic phases were roughly the same, which means there must be another reason why the growth was so large. And it turns out it's also very important what the orientation of the eigenvector is in relation to the magnetic fields. If you notice, here we're plotting a distribution of the angle between that eigenvector and the fields. What we found is that during the diffusion-free phase, there was much more preference for alignment and anti-alignment than during the kinematic phase. What this meant is that during the diffusion-free phase, the dynamo tended to stretch along the direction of the magnetic field more, which was causing much larger growth. So to summarize, the diffusion-free phase is an extremely important phase of the dynamo if you want to understand these sort of fast evolving magnetic field processes. We were able to tentatively confirm Shikoshikin's model of the exponential growth of the integral energies, the peak scales, and the amount of growing modes in the spectrum. By performing fits to our spectra, we were able to show that we had a varying growth rate, and that sort of deviation from expected behavior was possibly explained by increasing dissipation. We were able to attribute the faster growth during the diffusion-free phase to the fact that we had much more effective stretching alignment. Further investigations are still meant to be done. One important thing that we want to investigate is, if you recall the distance between the resistive and viscous scales, does that distance affect how long the diffusion-free phase lasts for? Does it affect growth rates? So those are all very important questions to ask if you truly want to understand this phase, the diffusion-free time. Thank you very much.
Great talk, thank you. So you mentioned that you start with some pre-turbulent initial condition. Can you talk a little bit about how you set that up? And then I'm curious whether, since this is sort of a transient phase, does that depend on the initial conditions at all?
So what we did is we actually initially ran the simulation without this fully developed turbulence to let that turbulence, fully develop. And then we took that developed turbulence and plugged it in as the initial condition. The reason why we wanted to do that is because we really weren't interested in transient phases with the evolution of the kinetic spectrum, because we were mostly interested in how the magnetic spectrum evolved. So right from t equals 0, we wanted to see that evolution of the magnetic energy.
So this was a very interesting topic. You base your results in a single simulation, from what I understood.
Yes, this was all in one simulation.
How would you expect your results to change based on the resolution of the simulation? Because that is a great code to numerical diffusivity could affect the turbulence and it could affect the problem spectrum.
Yeah, so that was another issue with these simulations, is because if you're setting up these parameters, those parameters can only be resolved on certain grid scales. And the larger PM you go to, you need more and more grid resolution, which tends to lead to more expensive simulations. But other than that, the main thing that going to higher grid resolutions would affect is potentially we would not see dissipation growing so fast because we were limited by grid size. The magnetic spectrum was actually very quickly able to reach the resistive scale. What that meant is it knew about resistance, and hence we saw that dissipation. So if we were able to go to more higher grid resolution, we would be able to increase our PM number and thus get a less diffusive evolution of magnetic spectrum.
Okay, this work was based on summer, or were you following up through the year as a just from the start, or?
This was sort of both.
Okay, so it was continuation. Very nice. Okay, well, thank you so much. And that actually wraps up all our presentations. And now we move to Daniela, where we're going to hear closing remarks from her. Then we have a very nice schedule of presenting certificates to the students and then taking pictures with them themselves. First, and then with the director, and then with the supervisor. And then we're going to go at 1 p.m. Have lunch in the CITA lounge.
Before we go, we should thank Joanna for stepping in and being the chair of all the talks and for the introduction.
Great.